So Laurent Ailleres, did I say that right? We were practicing so much.
That was better before, but that's pretty good still. Nobody can see it properly.
Well, thank you so much for joining us today to chat about the Loop platform. Laurent was initially trained as a structural geologist and awarded his PhD in 1996, having worked in the French Alps and from only meters away from the development of the Gocad 3D modelling package. Since 1996, he's been a research fellow at Monash University, where he leads the Loop initiative to develop the next generation of 3D geological and geophysical modelling tools.
So thank you, Jess, for having me. I think I'm very excited to talk about this project here. This is a project that's been going for about 3 years, properly funded, and probably started in 2010 as a PhD project here and there. This is the Loop project. I hope you have heard of it. If you haven't, then we've done a bad job. And this afternoon, as I was finishing my talk, I realized that I was probably behaving like a car salesman and telling you to come and listen to me talk about digital innovation for a greener future, where I'm actually going to talk about not something else, but it's actually not something we've done yet. It's actually a concept that we want to take on further. So what I'm going to talk about is the progress we've done so far in Loop and some aspects of it. And then I'm going to show you, or at least try to convince you that we can do the digital innovation for the greener future in soon. All right, so you may also have wondered what do I mean by a piece of code, so a piece of software for a greener future. So I think we all agree that for a greener future, we will need more metals. So we need the critical metals. We will need a lot of copper. We need to also, so miners are getting more and more automated. So you got those little trucks, or I should say rather bigger trucks, running along, automated, and digging dirt out of the ground and extracting metals out of that. Not the trucks themselves, but another process which is automated as well. The only thing in that bit that's not automated is actually geology. We take geology as granted. Well, actually, we're very bad at characterizing it in 3D, whether it's at the continental scales or it's at the man scale, even with a humongous amount of data. As a side job, I also run a consulting company for the mining and exploration companies. And each time I go to a mine site, it's very rare when you find a good understanding, like a robust understanding of the geology of the deposit. And that understanding is not better after I left. It's just that the status of our knowledge of our mines is very poor, which means that we're digging dirt that may not contain the amount of metals it should have, and we're digging dirt that may contain the amount of metal it should have, and maybe there is even dirt that we're digging out that has more metals than planned. And we mixed all of that into the process of extracting metals from the minerals. So if we had a system where we can characterize every little cubic centimeters of rock in terms of their geometallurgical characteristic, geotechnical characteristic, grade, lithology, etc., we'd have a system where we can predict better and feed the right rocks to the right part of the processing plant. So that's what we want to do. We want to develop a system where we're able to provide a model that is shared from the exploration stages to the processing stages and to the even the closure of the mine. So we want to know what's in the stockpile as well. We want to produce that platform where we can predict what's in the rock and help reduce the energy required to crush the rocks and the water required to process the rocks. So this is what we want to do in the future. This is what the title really talks about. And I'm going to show you how we're going to be able to do this. Basically, what we need to be able to do this is, without thinking about the characterization of the measurement of the parameters, it's a question of what we can do in the Loop project is interpolating those properties in 3D in a clever sense. So I'm going to show you how we can build 3D models. And then I'm going to show you why the way we build those 3D models will allow us to do property estimations. Before we go further, the Loop vision really is about creating more realistic digital twin of the geology. If we want to automate the extraction process and if we want to automate the entire value chain through exploration to mining, we actually need to automate geology. So we need a system that allows us to encode structural geology and geological concepts and use those concepts to interpolate lithologies and mineralogies and all these things. So for example, at the man scale, what we want to do, we want to be able to use the first drilling interceptions to optimize the next phase of drilling. So which directions, how deep should we be drilling? We want to propagate and calculate the uncertainty throughout the modeling process from the first drill hole again to resource estimations. And we believe that by doing so, we can increase our recovery rates. Some mines in Australia have an appalling recovery rate. I'm not going to name them because it wouldn't be PC, but there is a lot of wiggle room to improve the actual mining process for itself. That will increase the image of mining as in society, and that will also reduce the amount of resources required to extract the same amount of metal. So Loop, I'm going to talk about the founding of Loop at the end as a concluding slide, but basically the principle of Loop is to provide a solution, a platform for better management of our resources underground. So we want to provide a system where we have an increased confidence in the subsurface architecture, the subsurface property distributions, and that include lithologies and all the property I talked about before. And we want to make sure that the people making decisions have the best information at the end, and they also understand the uncertainty associated and the risk associated with their decisions. To do this, we have a multi-pillar approach, if you want. We have so what I'm going to talk about today, or in fact, part of what I'm going to talk about today, which is in orange here, that's the modeling engine. And we have a downstream and upstream modules. And in the upstream stuff, that we're doing a lot of things with the geological surveys from Canada, Australia, and in Europe. And basically building a geological ontology to be able to capture all the information that is available, and so that we can use that information to feed into the modeling engine. We are adhering to the principle of fair data and fair software. So fair on the side here means findable, accessible, interoperable, and reusable. And also what I want to emphasize is the software is actually open source. So everybody can contribute, everybody can use it, and there is no license. So we're really out there to grow the community. The downstream aspect of Loop is looking at, so this work here is done mainly by the geological surveys that are part of the Loop consortium. And there is also one aspect which I'm going to talk about today, which is Map to Loop, which is an automated way to analyze geological maps to extract information to be fed into the modeling engine to build 3D models. And we're going to talk about this a bit more details. So this work, Map to Loop, is done at UWA in the team of Mount Teso. In orange, in yellow, down here is the downstream aspect of Loop, which is looking at what do we do with the uncertainty? How do we use it? Can you tell us something about guiding us towards the acquisition of the next data in the right location to actually maximize our expenditure, to maximize also the reduction of uncertainty? You will see that we're going towards a Bayesian modeling system, which is a probabilistic modeling systems, where the modeling engine itself generates its own uncertainty and its characterization of the uncertainty based on knowledge and data. The orange bit in the middle, which is what I'm going to talk about, and I'm actually only going to talk about half of that, is the structural modeling engine and the geophysical integration. So we try to use geophysics not at the end of the process to falsify some of the models. We want to use geophysics to actually constrain the building of the model in an extreme sense. So for example, gravity may tell me that surface cannot dip in that direction. And I want to, if I know that from the gravity, then I want to use that constraint to prevent that fault to be dipping in that direction. I'm not going to talk about this today. This is the work that was done by Jeremy Giraud at UWA and Vitaly Ogarko. And Jeremy has now moved on to Nancy, which is also a university, Nancy in France, which is a university we collaborate with as well. What I'm going to talk about today is Loop Structural and Map to Loop and Loop Structural, which is our modeling engine. So quickly, these are the people that are involved at a high level. So there is people in the steering committee, so representing the different organizations. I'm not going to go through all of the names, and these are the people that actually do the research and develop the software. These are the module leaders of the different aspects of Loop, and today, so I'm going to talk essentially about Loop Structural and Map to Loop, and not Map to Loop. Yep. So Map to Loop is a system where we want to automatically analyze geological maps. So you got an example down here on the bottom left corner. And what we do is basically do a geometrical analysis. So we look at the contacts and the strike and dip signals, so the structural information, and infer or guesstimate, if you want, or estimate the thickness of the different formation throughout the entire map and define an histogram of distributions of those thicknesses for each lithologies. We can also do an assessment of the fault offset. So it's an apparent fault offset based on the displacements on the map and also taking into account the depth of the formations. We also do a topological analysis, which will build the stratigraphic column. So looking at which units are on top of each unit and the type of relationship, the type of contacts, whether it's a conformable contact, an unconformable contact, or a faulted contact, or an intrusive contact if you have intrusions. And we also look, of course, at the relationship in the fault network. So which fault cuts which faults and which fault cuts which formations. So all this is done automatically as long as you have the right data served by the geological surveys at the moment. So you basically have to have your structural data, your which are points, your lines, the polylines, which are the faults, and then the polygons, which represent the lithology. So this is on the right-hand side here is an example of normalized thicknesses to look at the distribution of thicknesses calculations along the contacts. So that gives us an estimate of the variability of thicknesses per formations. And you will see this is important to actually capture that a priori information, that a priori posterior distributions of properties per lithologies for the Bayesian modeling at the end. And we also estimate or guesstimate the apparent offset of faults, at least from the map pattern and the strike and dip information. In terms of the topology, we end up with a graph which represents the different spatial relationship between the different formations. And so this example here is from the Hamersley Basin, and we're looking at the RNO formations and things like this. But we're looking at the type of contacts between different formations. The arrows point to an older unit, and the colors correspond to the type of contact. So the blue contact is conformable, red contact is faulted contact, and then the thickness of the arrow is actually the length of that contact on the map. So you can grab a lot of information out of map2loop just by building those graphs and visualizing the results. We do the same thing for faults. So all of these little rectangles here are faults. They classify, so the rectangle correspond, the color and the size correspond to the size of the fault based on the length of the fault on the map, if you want. And all the arrows are the type of relationship between the different faults. So you can end up with very complicated graphs. This is actually unreadable. It looks pretty cool, but it's actually pretty useless unless you have a system to read that graph and then be able to generate a history of deformation or history of faulting of the geology. And we can then feed that into the modeling engine. And then here, something a bit more easier to read, or something easier to read, which is the relationship between the faults as columns. So all the numbers there are number of faults, or the fault number, the ID of the fault. And the lines are all the different formations, and whether if it's a green, so if it's a flag, it's 0 or 1. If it's green, basically the fault is affected by the formation is affected by the fault, and if it's red, then the formation is not affected by the fault. So it gives us an idea about the extent of the faults and also their the time span. So all this information can be fed into Loop Structural, which is our modeling engine library, and we've done demonstration or examples from all the states in Australia. And so all you do is basically you as long as those three files are served, you can draw a rectangle, and you then press a button, and after a few minutes, you get a model. So everything is automated. We extract all this topological information, the structural information automatically. We build a stratigraphic column, also using the Geoscience Australia stratigraphy database, and then your models is built automatically. So this is an example here from WA, the Flinders Ranges in South Australia, etc., etc. What's pretty cool about this is it takes about 11 minutes to build. So this model here, South Australia, the Flinders Ranges, I think I built a very similar model in that part of the world, and it took probably about 11 minutes, or even let's say 25 minutes or 30 minutes. And I've been building models since I was born, maybe not, but since 1996. And a model like this to build by hand with the current technology or the technology before implicit modeling would have taken about 3 to 5 weeks to build. And it would not have been looking that good either. So this is amazing. The technology has been developed by the group, I guess. Yeah. So now what I'm going to talk about is how do we build those surfaces and why are we different from the commercial packages? So the current commercial packages that do that kind of modeling only use one scalar field. So a scalar field is a scalar field, and basically it makes sure that all the formations are conformable, and it only builds one scalar field per conformable series of geology. We use 3 scalar fields per object, per geological object. So a fault has 3 scalar fields attached to it. A fold or a folding event has 3 scalar fields interpolated through the entire volume of the model. Intrusions, the same thing. We have 3 scalar fields interpolated, and we call these 3 scalar fields the structural frame. So the structural frame is made of 3 axes, which are rectangular, so they're perpendicular to each other, and they're defined by the finite geometry or the finite strain definition of the object. So for example, for a fold, we have the main orientation is perpendicular to the actual surface. So there's a plane of symmetry of the fold through here, and that basically runs a coordinate system perpendicular to that actual surface. For the fault is going to be the fault surface, defining that. So a normal to the fault surface is going to be that major structural feature. Then we have a structural direction, which is a fold axis in yellow here into the page for the folds, and for the faults, it's actually the direction of the flow, which is not always down deep, obviously. And then we have for the intrusions, that the structural direction is given by the flow direction. So we need to know some information about the object we want to model, which are based on processes, but we're not modeling the processes. We're modeling the result of the processes. And then we have a third direction, which is basically perpendicular to the other 2. And in the case of the fold, for example, this will be the extension direction. So I'm going to show you how we do this for each of these different elements. And we're starting with a fault. So a fault is defined as a damage zone, is defined as an ellipsoidal damage zone for which the decay of the flow is actually given through those graphs. So which is so along the fault with a long section along the fault, and that's a cross section across the fault, and that gives you an idea of how the fault throw or offset decreases away from the fault. So at this point, at those right points here, the offset is actually 0, so the fault only exists within that damage zone. And the flow is also defined perpendicular to the fault surface through here. So that's another definition of the fault flow, where you got this side is being dropped and this side is being moved upwards. The advantage of doing this is we're actually using kinematics instead of the current packages use the step function. And the step function is just pumping up the value of the scalar field by a given value that coincide with the stratigraphy on both sides of the fault. We are actually using a system which allows us to follow the shape of the fault. The way it works is if this is your observation, so you have a fault in black through here, and you have 2 observations of a stratigraphic horizons on both sides of the faults. Of course, intuitively, you want to have a normal fault doing this. What we do is we restore the offset. So we assume we know the offset. We restore the offset. We restore the position of the observations according to that offset. So this point would come here, and then we interpolate the stratigraphy, and then we reapply the offset in opposite directions. So the vectors through here are following the shape of the fault. So here is an example of a listric fault. You can ignore what's in the hanging wall of that fault. This is just a visualization issue. Or if you want, the arrow should go the other way, basically. And this is a vector field of displacement interpolated for a curved fault. This is here the field, the fault displacement again. So positive and negative on both sides of the fault. The fault will be through here. And the resulting 3D models showing that there is deformation also the stratigraphy related to that damage zone that the fault is associated with. And that's something that current packages just do, it's just an offset basically. Or not just an offset, it's just a discontinuity in the model. We've done a lot of work on intrusions as well. Also, when I say we, it's actually Fernando Alvarado, who is a PhD student at Monash with Laurent Ailleres and myself. The work I showed before was actually the work of Laurent Ailleres as well. And here is an example here of a seal propagating into the plane of the screen and developing those what we call those steps. So you can see that the seal is actually stepping up stratigraphy and using the anisotropy by the stratigraphy to actually propagate. And in this case here, developing, I think, what we call the broken bridge. And so we want to use this understanding of how seals or intrusions intrude, including plutonic intrusions. And so using the anisotropy in the rocks, we want to use this anisotropy to constrain the geometry of our intrusions. So what Fernanda has defined, she's defined also an intrusion structural frame, which I think is in the next slide. Oh, it's gone. Wait, there it is. I'm not sure what happened here, but it doesn't matter. And the structural frame for the intrusions is defined as a direction. So the direction of propagation, you can see the intrusion down here. If you follow my cursor, this is the way the intrusion was propagating. And perpendicular to that direction, that propagation directions, you find those pink planes, which represent the P directions, or the P part of the structural frame, which is a propagation direction. In green, you have the intermediate directions, which is a line itself with the propagation directions, but refers to the lateral extent of the intrusions. And in orange, in G, you have the thickness of the intrusion. So it's basically looking at the gross directions of the intrusion itself. And if we can interpolate thicknesses or some parameters of the intrusions in that frame, we end up with an intrusion that fits our data and also fits our understanding of the processes of intrusion. So here is an example, that's a synthetic example where we have flat stratigraphy offset by a fault. And the points down here represent the base of a seal propagating, and you got points down here as well. And you may not see, but you should see that there is actually two sets of points for the base of that intrusion, which are also offset by the faults. So basically, we're looking at an intrusion that arrive at an intrusion at a fault surface, and one segment actually developed on top of the other two segments, and related to the fault and the anisotropy represented by the fault. So the model, once you've calculated all the structural frame for the intrusions and fitted to the data, looks like this in long sections. So the same section as this one here. And you can see that you got two levels of intrusion here, and it's coalescing before the fault. So that would be done here. And these are two top views of those three lobes basically developing just because of that fault. And in cross sections, so this is the same view here with cross sections. In cross section, you can see the outline of the intrusions with those fine lines. And you can see that we are developing those stepping segments that can propagate separately. And as you come closer to the southern end of that intrusive body, you end up with coalescing segments and broken bridges and the structures you actually see in the field. So this is just using the constraints of observing, knowing how, having some assumptions about how intrusions intrude, and also using the anisotropy in the host rock. For the folds, we use, as I said, we use the finest strain orientations of the fold, so the actual surface through here, and we define a coordinate system perpendicular to that actual surface, which is represented here from 50 to minus 50 to 0. And in that orientations, we're going to plot the orientation or the angle of rotation of the folded foliation with respect to the orientation of the folded foliation in the hinge. So in the hinge, it should be 0, and in the limbs or in the inflection point, this is going to be the maximum angle of rotation of that folded foliations. So for isoclinal folds, you would expect that value to be minus 90 and 90 on both sides of a hinge. So you end up with those points down here if you've measured a lot if you've taken a lot of measurements. So this would be in one of the limbs. So it would be on one of the limb here, and the other measurements come from the other limb. As you can tell, we've taken no measurement in the hinge, and this actually produces the most uncertainty in the interpolation. Once we've got this, we then interpolate a Fourier series that fits the data, and then they can propagate the wave of folding throughout the entire model. And of course, you can use this to fold previously calculated scalar fields. Yep. So and this is my segue to talk about how do we actually build models of areas which have suffered a protracted deformation history. So each of the objects or each of the events, and an event can be a fault. One fault is an event, or a family of faults is an event. Folding is an event, and you can have multiple folding events. Unconformities and intrusions, each of them are an event. And by this, I mean that each of them happen at a given time. So loop is a time-aware system where we start with the youngest deformation event and then go back in time. So there is an aspect of it that tells me that we could do reconstructions as well in 3D. But I think we don't have enough information to do this, and we can't really quantify the volume variation during deformation as well. So I'm going to show you an example for foldings where we have two deformation events, two folding events. We would start with the youngest foliation, so our S2, or the second deformation event. And that S2, if there is nothing happening after it, should be planar and regular and represented by this scalar field through here. We then use this scalar field combined with the observation of the foliation, the next youngest foliation, so S1. And if we combine this foliation, so S2 scalar field with the observation of S1 into the plot that I was talking about just before, we can then interpolate our fold profile, which is this thing through here. And once we've done that, we can then interpolate that fold profile throughout the entire volume. So it gives you something like this. And then you can combine this scalar field with observations of the next youngest foliation, which would be our bedding in this case, so S0. And using S0, we then also are able to interpolate or fit a Fourier series to the data and define this fold profile through here, so recumbent fold, whatever. And when you combine this with the results, you end up with something like this, where you can see you got a refolded fold throughout the entire volume, not just where you have the data, but throughout the entire volume. I actually don't show you where the data are, but I should. So these structural frames are very powerful in being combined. So in multiple ways to build complex geometrical models. Yeah. So here is an example again from the Hamersley Basin. On the left-hand side here is a model with faults and some folding. It took 15 minutes to build, so 6 minutes for the automated map interpretation, 9 minutes for the actual building of the model. And you can then display the model and compare it with the geological map used for building the models. So the lines here correspond to the polygons of the maps, and the polylines of the faults, and the color correspond to the prediction from the modeling. So you can see that there are some errors. So for example, down here there is an issue with one of the faults is not respected properly. And that comes from the fact that in this model, all the faults are assumed to be vertical and to have a down deep offset. And that's something that this is the information we have. So for building this model, the one model, we just had to assume some parameters for the fault. But Lachlan has been working very hard recently, and basically we're looking at Bayesian system to try to infer the parameters of the fault. So we at this stage, this slide only shows when we look at the displacement of the fault and the direction of the fault in the fault plane. So we have an example up here, which is very simplistic. It's basically a fault in that gray surface, a vertical fault if you want, it doesn't really matter. And then we have peaks of two horizons. And what we want to resolve is the direction of flow and the amplitude of the flow to reconcile those data points in a plane. So both the yellow points on both sides of the faults and the blue points on the both sides of the faults should be reconciled into a flat surface, in two flat surfaces. And when we started doing, well, when Lachlan started doing the Bayesian approach to try to estimate what was the parameters in terms of pitch, and so pitch, the direction of the flow, and the displacement, he ended up with this very nice figure here, which I wanted to show because it's Friday and it looks like a smiley face. But it's basically showing you a cross probability diagram indicating which parameters would be the best to fit the problem. So we're looking at inverting geological parameters to get geometries. The beauty of using a probabilistic approach or a Bayesian inference is actually we can also capture the knowledge from the user. So for example, if I had a geologist who's been in that area and tells me, oh, I think the flow should be between 100 and 200 meters, we can actually put that as part of the distribution function. So as part of the a priori knowledge for the inversion. We've done the same thing for folds. And in this case here on the left-hand side, we have a fold, which is marked by the repetition of stratigraphy on both sides of that red unit. And that fold is then overprinted by dextral shear. So we know, or we just assume, or this is a given parameter, is the direction of flow is horizontal. But what we don't know is the actual parameters for the fold and the amplitude of the flow. So the parameters for the fold are all the Fourier series coefficient and the wavelengths of the folding, and the parameters for the fold is just the direction of flow. So if you use those parameters in a Bayesian inference and try to get a best fit with the actual data and the initial map, you end up with those cross plot of probabilities between the different parameters. So in this case, you have C1, C2, and C0 are the Fourier series coefficients. The fold wavelength is at the top here. And at the bottom down here, you got the fold displacement, the fold wavelengths, and the Fourier series coefficients again. So if we look here, for example, we would have the cross probability plot between the fold displacements and the fold wavelengths at the top here. So we can see that there are many different solutions. Some are more probable than others to fit our problem in terms of those different parameters. That allows you to actually calculate multiple iterations of the model. And this is an example here of the fold profile resulting from those different probabilities. So a point here may correspond to a point here, etc., etc. And we can calculate all these different models represented by this plot through here. And you can see that away from the data, you have an increase in uncertainty. So the width of that curve is just representative of how many curves there are, where when you have data, the problem is actually better determined. And so using those kind of systems, you can guide the next iterations of data acquisitions to reduce or maximize the uncertainty reduction. So I am almost about to conclude because I think it's time. We're going now to talk about loop resources, and loop resources is our way to, I think, improve the way we mine and to provide a 3D model of the geology. And when I say geology, it's all these properties we talked about as a start, to hopefully improve the way we mine and reduce the mining footprint. So reduce the energy consumption, reduce the water consumption, and also improve our recovery rate. So Loop itself provides an automated, updatable workflow to model geology based on structural geology rules and based on our best understanding of the geology processes. And it also provides a characterization of uncertainty. So we want to be able to propagate our knowledge of the uncertainty, or propagate what we don't know, basically, or the quantification of what we don't know through the modeling process as well. So we have a better idea of an educated way to make decisions. But Loop, actually, the way we've used those structural frames is provides us with a framework to model properties, because it provides us with a curvilinear coordinate system, curvilinear rectangular coordinate systems, to be able to do geostatistical characterization of property variations in curvilinear domains. So if you have, for example, a recumbent fold going this way, we're going to be able to unfold that domain, do the geostatistic in a Cartesian sense, and then redeform it into its actual form, which means that we don't have to have one semi-variogram for one property for the entire model, but if we use proper domaining and proper structural geology modeling, we can use these geostatistical methods to interpolate properties in very complicated volumes, following the shape of those volumes. Not sure I'm very clear here, but yep. So this doesn't want to appear, but what I was talking about is for each of these different objects, and conformity has the same, etc., etc., we have a Cartesian curvilinear model. Yes? So that means that our uncertainty will be not uncertainty, our estimation of properties and the geostatistical characterization of the variation of the properties will follow the shape of our deformed layers. But then they can be treated as a Cartesian volume when we want to do the estimations of distances and things like this. So a piece of code for a greener future. I think this is the missing link in the automation of the mining process. I think the automation of knowing geology is lacking, and this is where this is what we're working towards. We need a better ore body knowledge in 3D. So that means we also need to develop the method to characterize what we want to interpolate in 3D. And so that's not our job. All we want to do is be able to take those characterizations and interpolate them in a clever system that understands geology. So I go back to the loop vision. We want to create more realistic digital twin of the geology at all scales. I think at the scale of the belt, we've done a very good job so far. We've only been going for 2.5 years. And at the man scale, I think it's just a question of applying and understanding how to deal with the huge amount of data available and data that is actually not very consistent to start with. Yeah, so I'm going to keep on going. At the end of the day, Loop is only going to be successful if people start using it. So Loop is not only a piece of code, but it's actually a community. And these are pictures of our research meeting we had in Basselton in 2020, just before lockdown happened. So I flew from Perth and went into lockdown straight away in Victoria, and I feel like I'm still in lockdown since then. And so the people are very important. So we encourage you to come and work with us, to do research with us, and to use the platform and tell us what doesn't work and what does. And to finish, I'd like to thank all our sponsors. So on the project is being funded by an ISA linkage, supported by the Geological Survey of Australia. The project actually initiated from One Geology and Chris Pygram, who was at the time the CEO of Geoscience Australia. And I guess without them, there would not be a project. We would still be doing PhD projects here and there and having fun. And now we're having fun, but with way more people. On the left-hand side here are the research organizations. So we are working with people in France, Germany, England, so all over Europe, basically, Canada, and of course, Australia. And so the project is also funded by the MINEX CRC with the involvement of again, the Geological Survey of Western Australia, BHP, Macroman, and Anglo-American. And recently, these are new partners, and that means that we have all the state and territory and federal Geological Survey of Australia are supporting us. And we also have the support of the USGS and CSIRO and more people in Europe, so from the University of Orléans in France. I think this is it. And yep, thank you very much for listening to my ramblings.
Thank you so much. That was really cool.